Okay, so straight to it. My aim in this talk is to stick to the abstract which I sent in, which is really to try and establish some foundational relationships that underpin the establishment of chirality, the detection of chirality, and whatever you can do with it in various kinds of matter. So I need to position myself so I can see. Yeah, here we go. So I want to point out, first of all, that the different manifestations of chirality have no absolute measure. It might be nice to think that you could say, here's some chiral matter, here's some chiral radiation, I'm going to have some sort of conservation, or that isn't ever going to work. Not least because optical measurements on matter will usually depend on the specific wavelength or wavelengths, in the case, for example, some frequency generation that you use. Also, we're going to look at the sense of scale that's involved in measuring chirality. And then I'm going to say, is it not coming through? Okay. All right. I'm going to look at the multipolar foundations for interactions that are chiral, and say a bit about where they come from. Look at some symmetry principles and a little bit about some possible methods of chiral separation. And then at the very end, just give some other thoughts that occurred to me that I might like to share with you before we conclude. Okay. So let's start with the basis. I mean, chirality, it was originally, I think, detected. Louis Pasteur separated crystals by hand and found there are left and right-handed forms. What is a chiral molecule? It's something where the nuclear configuration has a point group symmetry representation that includes no improper axes of rotation. An improper axis of rotation is a rotation and a reflection combined. So that includes mirror planes and inversion symmetry. If it lacks those, then it will be chiral. In chemistry, we have typically things which are chiral will exist in one of two forms. They're called enantiomers. And the differences between them, which are usually very similar in their chemical properties, only arise when they interact with other chemical entities. So, for example, there are some quickly run through some well-known ones. Pharmaceuticals is a particularly important one because thalidomide, it's well known what the upshot of the thalidomide disaster was when a racemic mixture, that is, mixtures of left and right-handed molecules, were administered to patients. And one of those enantiomers is entirely safe, but the other isn't. And because that wasn't recognised at the outset, there were these embryonic deformities caused. There's ibuprofen, on the other hand, is a molecule which also exists in but left and right-handed forms, and in fact is sold as a mixture because one is effective, but the other one it doesn't do very much, but it's not toxic either. And then we have things like in fragrances, there's molecules here with the left and right-handed form with entirely different smells, which signifies the fact that the smelling apparatus must itself be chiral. Okay, now I mentioned the issues of scale. If you take something like a protein, it's built up at a fundamental level from amino acids. Most of those in nature are left-handed, and if you look at a unit like that, you can see the way in which those atoms are formed together confers a left-handed configuration. But they are wound up into things like alpha helices and beta sheets, and the alpha helix forms are mostly right-handed. So at a different level of scale, we have an entirely different sense of the conformation there. Those also are typically wrapped around into something which ends up mostly fairly globular and has a tertiary structure, and that can again have a different configuration. So sense of scale has to be signified when you're talking about chirality, at least a sense of it. And also just notice that anything amorphous, I mean, you pick up a regular potato or even the vaterite particles that were mentioned earlier, if they're not exactly spherical, they're probably going to be chiral, even if they were internally not chiral. Okay, what are the challenges? Let's look very deeply at where this chirality comes from, because it's ultimately, especially when you're looking at optical interactions with matter, it's to do with the way in which the charges in those molecules interact with the radiation itself. If I have two dipoles and they're both in a plane, that's not going to do anything chiral because I can take the resolvent of the two and it adds up to just some other dipole. But if I pull one out and make a three-dimensional object like that, then that can form a chiral entity. And in fact, this was one of the earliest models of chiral behavior. Two electric dipole moments pulled apart, so in a non-coplanar configuration. That will work if the optical frequencies with which those two groups, if it's two components within a large molecule are chemically equivalent because they then have the same optical frequency for absorption, for example. That's the Kuhn and Kirkwood model of chirality and optical rotation. What he got there is, if you look at it, it's a combination of a twist and a pull. It's a translation and a rotation, and that's a kind of a motif for optical activity. And if you look at the molecule with these two pulled out dipoles like that, you can also see, if you pull it around a bit, that it's going to have some sort of quadrupolar aspect to it as well. So magnetic dipole and electric quadrupole, we're going to look at this a little more deeply. I mentioned issues of scale are important in determining how you describe a chiral molecule. Also, it has a bearing on the way in which you measure it. You can get, for example, chiral near fields in achiral, that is non-chiral, plasmonic nanointel. There's some nice work published by Schäferling and co. in 2012. It just basically shows that if you have something that you come in very close to, even if it's not intrinsically chiral, then you may signify the near field a chiral character. Again, it's an issue of scale. Is that the answer for why or whether or not all optical angular momentum can get involved in chiroptical interactions? Not really, no. I think it was possibly thought that originally, but it's something much deeper than that. Actually, also, I remember Michael Berry showed me once, he's got a very nice model, I think I'm right, Michael, of a Lego construction that has a left-handed twist there it is, yeah, look, he's holding up, in the local dimension, but it's twisted around into something of the opposite conformation in the other sense. Once again, a reminder that we need to know what the scale is when we're talking about chirality. Okay, let's get deep in then. So if you're looking at how light interacts with these charges, we've got radiation with electric and a magnetic field. I'm going to use a quantized field representation, although the classical picture alone is quite misleading. And the reason I say it's misleading is because each of those things, the electric field and magnetic field, and also the things that are associated with it, like vector potential and so on, they all have characteristic parities which are not apparent from that kind of depiction I just showed you. If we start with the vector potential, it's a negative parity with respect to time, even parity in space. No, sorry, negative in space rather. And that correlates with the fact that if you take the electric field, you get the correct behavior, which is time even, and obviously space odd. Magnetic field, conversely, with the curl of A, it does the opposite. The pointing vector does what it should do, although I won't go into exactly whether that registers precisely momentum at the moment, so that's in the light of what was said yesterday. But also, if you look at the couplings, then you can see that, for example, well, just to show you here at the top, that we start with minimal coupling Hamiltonian. A canonical transformation leads directly to this form in which you have this series of terms. So this is going to work with so you have a series of all the electric multipoles are contained within that term, all the magnetic multipoles in this one. There's the first two terms, and that's E1 and E2, let's say, electric dipole, quadrupole, the first term in the magnetic series, which is a similar order actually to this one. But if you look at the couplings, then, for example, because the Hamiltonian is an energy, and it's obviously time even and time even and space even, then it's necessary that the electric field interacts with multipoles of this kind of character. And equally, the magnetic ones interact this way. Oops, let's get that there for a second. In between those, you just see I've put down the fields of particular modes there. You have to bear in mind that when you have a field expansion, you've got a complete Fourier series decomposition of the field there. It's an operator form, but the point is that any individual mode can have a symmetry which is not the same as the overall electric field. So Gaussian modes, for example, have this character for the temporal and spatial symmetry. Okay, within the paraxial approximation, we know how this works. I'm going to run through this because it's quite familiar, but essentially the orbital angular momentum, at best, in the ideal circumstances, can be separated out into something which resolves as a sum of the operators for the numbers of left and right-handed photons, whereas the spin angular momentum is the difference between the number of left and right. And that appears to represent a sound basis for compartmentalizing electromagnetic observables. Okay, that's some work that I did with Matt Coles back in 2012. Just to get right in here, let's look. I mean, the QED that we use, and that is used for specifically molecular applications usually, but which is extendable to downward in scale to atoms and upwards to nanoparticles, is a non-covariant formulation. The charges move at less than the speed of light, much less than the speed of light. It's pretty good for applications to nonlinear optical and photophysical applications, and it does deliver things which relate to experimental observables. These are kind of bullet points I have to put up whenever I'm giving a talk and explaining why QED is a good thing to use. In particular, though, going back to this multipolar thing, it's just worth emphasising that all interparticle interactions are mediated by virtual photon exchange. This is an exact representation of the Hamiltonian for a system of particles. The radiation Hamiltonian is a distinctive feature of quantum optical formulation. Of course, sum over all the particles, everything which is electrically neutral can be summed up, but it's Schrödinger operators there, and the interactions of those particles with the radiation field. There's no term that connects one of those particles with another, so all those things are mediated by coupling through the radiation field. And Craig and Thurmachandran's book goes into that in great detail, as several others do, but few others so elegantly, I think, as that one. So the radiation Hamiltonian commutes with LNS in the ideal conditions, so it does give us a confidence that we can specify optical states with respect to energy, frequency or wavelength if you like, spin polarization and optical orbital topology. And then we develop the theory for particular interactions through a perturbative expansion of this kind. We've got a sum of matrix elements for every individual particle. And although this gets a little bit horrible, for a process involving n concerted photon interactions, which were the nth term in this series here, then you have essentially the matrix element is constructed from a contraction of a radiation tensor and a molecular tensor, and this comprises sums over all possible combinations of orders for the various electric and magnetic multipoles. And a chapter that Mohammed and I wrote in this book goes into that in detail if you want to look further. Okay, that's what I said. There's what you have to build in if you're looking at topological charge. So the parities of each paired S and T must be the same in order that the product is a scalar energy. That's the foundational symmetry principle here. Energy, time even, space even. You can have a time mod and a time mod for S and T or whatever, but the product has to be right. However, this thing is going to be taken into a square when you're looking for a rate. A quadratic term can have an interference between those different parity contributions. Oh, okay, that was quick. So circular dichiasm, for example, is something where you have a difference between the absorption rates of left and right-handed light. Here's a thing with threefold symmetry. It's chiral, and you can see that the dipole and the rotation in the same axis transform under the same representation. Therefore, a mu and an m, a transition electric and magnetic dipole, can combine. And the helical form is as we've seen, comprised of that kind of combination. Here's an example of an organic component. Was that 15 minutes? Was that? Oh, okay. Here's an organic component that absorbs differently at two different wavelengths for two different transitions. One is magnetic and one is electric. That's not chiral. But when you have the same transition resolved in this way, so there's the operator for electric dipole. Here's the operator for magnetic dipole. There's the Q cross P, angular momentum there. It's this. It's something which is associated with an axial vector, because if you invert space, then the displacement vector and the P change sign. So magnetic is axial, and of course the electric dipole is a polar vector. So electronic transitions in chiral molecules have to accommodate both electric and magnetic dipole forming the same transition. And the product of those two things is a pseudo-scalar, or if you take a product of their components, it's an axial tensor. Okay, so for example, that's what I just said. There's this is taking the imaginary part here of the transition electric dipole and the transition magnetic dipole, 0 to n, m back to 0, it's basically the same transition. That specific thing is trace, plays a role in optical rotation. It also plays a role in this issue. One recently proposed method to separate chiral molecules, similar to optical rotation, except it involves the off-diagonal elements of that tensor I just shown you. It's a process in which the initial and final states are the same, and so we work out energy shift by taking this expression here, and then we will get the force by taking the gradient. It's a gradient force from this. And the chirally sensitive part of this, which is to say the difference in the rates you get for left and right-handed molecules with a given circular polarization, or conversely different polarizations with the same chirality of the molecule, are determined by this expression. Oops, I was going too far there. This expression there. There's the force. And what we wanted to do is to just be honest about whether this is likely to be a practical method of separating chiral molecules. Because if you can do that, as we saw at the outset, the nature of the different properties of chiral molecules, left and right-handed forms, can be absolutely crucial. They're quite hard to separate. The pharmaceutical industry spends a huge amount of money trying to do exactly that. Well, to use the methods that we proposed, you probably would need, ideally, to get the molecules in the vapor phase. Vapor phase pressures for large molecules, such as we're interested in separating, are very small. If you use high temperatures, you get a thermal degradation. So it's not likely to be useful for biological or pharmaceutical molecules. Liquids or solutions, we could envisage, and we have envisaged something of this nature. Suppose you have both enantiomers in a solution, and you send, let's say, just a straightforward Gaussian beam through, then it's true that one enantiomer will have a slightly larger optical force towards the center of the beam, highest intensity, than the other. And the enantiomer with the larger force will displace the other one, and then we can get a time average difference in concentrations. Vortex beams could be used, but you don't have to do it. It looks like this. So there's the input beam. Both configurations of molecules are there in the center. They're both being pulled into the center, but if there's a competition for space, then actually the differential will push one towards the outside. So yeah, the right-handed enantiomer in this configuration, as I've shown, is more likely to be on the periphery. Well, that's our conjecture. But the effect is going to be very small. If I'm allowed to, I'll just give one brief thing, which I added early hours of this morning. I was trying to explain the underlying principles here, and it has to be borne in mind that sometimes things militate against anything being quite so neat as one might hope. This still looks very good, linking angular momentum with chirality, as I've been intending to do in the talk, and we can see how that would work for things like regular fluids, anything where you've isotropy on the bulk scale. Exceptions arise when you have something which breaks the symmetry, as for example a surface, and there's a very nice example in this work by Janice Hicks' group. It's quite old, it's 1993, but they showed how chiral molecules, or put it this way, a surface in which you're looking at second harmonic generation by reflection using circularly polarized light exhibits a differential effect, which is only due to electric dipole interactions. It doesn't involve magnetic dipole, electric quadrupole, or any of those things, so it's actually quite large. So it arises from hyperpolarizability, much larger than you expect from the kind of thing I've been showing you there. How does that work? Well, it actually comes down from the imaginary part of that tensor. It involves the dissipation that Michael talked about in his first lecture yesterday. It's a damping of the optical response that's usually associated with line broadening mechanisms. Under those conditions, what you've eventually got, the thing is going to break down because you have a non-Hermitian Hamiltonian interaction operator, and therefore time reversal arguments, time parity arguments don't hold in the same way that they should do in the regular systems I was describing to you before. Okay, so that's a passing thought. And if you're interested in some of our views on these things and thoughts, two of those articles that have come out in the last couple of years. So these are the people who've done most of the work on this subject. David Bradshaw, who isn't here today, but he's going to be in San Diego next week. Jamie Leader, that's Matthew Williams, Jack Ford, Kane Forbes, and Matt Coles, also who's not pictured. These are the funders. We were glad for it when we got some, and thank you for your attention.
So your point is that no matter what we do with light, we cannot do chiral separation in liquids.
No, I wouldn't say you can't do it. No, I didn't say you can't do it. I think the effects are there, but they're very small. I find it hard.
Brownian motion just covers all.
Brownian motion is obviously a major issue for that kind of thing. Yeah,
so
sure.
no superchiral fields, no vortices or something.
Superchiral fluids. I hadn't thought about that one. I don't know. Yeah, sounds good. Anything with super in is always good, you know.
But I think it doesn't work. It's just the resonances of the two.
These things are yeah, absolutely, very small. Yeah.
Thank you, David. I
Thank you.
think in the interest of getting to our lunch on time, let's head it out. Thank you again, David.
So, good morning. I'm going to describe work I published last year together with Steve Barnett and Alison Yao on what we now call the chiral optical force. There's some overlap with what's already been said here, but I hope you'll appreciate at least a different perspective, even if it sounds a little bit familiar. So first, I'll say a few words more about chirality and why it's important. Then I'll explain what the chiral optical force is, and finally I'll outline some of the applications we have in mind. So chirality, of course, is the notion of handedness. We say that an object is chiral if that object somehow differs from its mirror image, much like a human hand, for example. Indeed, the word chiral comes from the Greek for hand and was introduced by a fellow Glaswegian, Lord Kelvin. There's his original definition, and like many interesting things, it appeared in a footnote. So chirality isn't just restricted to human hands, of course. Indeed, it pervades the natural world, from the unusual preferences of the electroweak interaction right the way up to the arms of individual spiral and elliptical galaxies. Chirality really is everywhere. In particular, many molecules are chiral and can be found separately in either left or right-handed forms, which are distinct mirror images of each other. So remarkably, these distinct mirror image forms often interact differently with living things. For example, the right-handed form of carvone is found in caraway seeds, so it has very spicy taste and smell. The right-handed form of methamphetamine is a harmful narcotic, and the right-handed form of misoprop is employed as a herbicide, a weed killer. In contrast, the mirror image form of carvone is found in spearmint leaves, so it has a completely different taste and smell. The mirror image of methamphetamine is perfectly legal. In fact, it's employed as a decongestant. And the mirror image of misoprop is ineffective as a herbicide. So such differences arise because chirality is also inherent to life, as we heard. And it's through such differences that molecular chirality drives much of its importance. So to give you but one representative number, unichiral drugs have generated in excess of $200 billion to date. So before moving on, I just want to go on a little tangent, if you don't mind. The dinosaur Stegosaurus exhibited exterior chirality. You can imagine that the largest plate, for example, tilted either to the right or to the left. So two distinct forms of Stegosaurus are conceivable, much like you can have two distinct mirror image forms of a snail. So believe it or not, I've never seen this recognized explicitly in the Stegosaurus literature. And indeed, I can tell you that one of the views of the Stegosaurus stenops holotype on display at the United States National Museum during the First World War had the wrong chirality. So moreover, it seems to me that most specimens were of the R form, but there is evidence to suggest that the L form also existed. So moving on to the chiral optical force now. So consider first, please, a small achiral molecule moving slowly in the presence of weak, monochromatic, far-off resonance light. So the light exerts a force upon the molecule, the cycle-averaged, rotationally averaged form of which follows from the Lorentz force law as this, basically. So F primed here is the contribution to absorption and such things. By assumption, that's small here. And what we're left with is this A grad W piece. So A is a property of the molecule. It's essentially a polarizability. And W is a property of the light. It's essentially the intensity, a measure of the amplitude of the light. So this is none other than the dipole force that's used in optical lattices for atoms and in optical tweezers. For molecules, it's been used in the Newtonian regime to deflect beams of molecules using the tail ends of Gaussian beams, and even in the de Broglie regime to diffract molecular matter waves using optical standing waves. So really, the main point of my talk now is that if you consider instead a chiral molecule, there's an extra contribution to the force where there would otherwise be nothing. So this extra piece here. B is another property of the molecule, essentially a polarizability, and H is another property of the light. It's essentially a helicity density. It's not a measure of the amplitude of the field, but more the twist of the electric and magnetic field lines. So this extra piece has exactly the opposite sign for the mirror image molecule. So it discriminates between left and right-handed forms, and it's this that we call the chiral optical force. So I want to say here this extra piece was recognized by some other authors independently at the same time, and they've gone in a slightly different direction with it, but I'd be glad to share those references if anyone's interested. So B is much smaller than A. This is not a large contribution to the force, but it's nevertheless possible to isolate it in principle by choosing light for which the intensity is uniform, but the helicity is not. Then you have no dipole force, and all you're left with is the chiral force, which acts to accelerate your opposite enantiomers in opposite directions. So an example of such light is two beams of light with orthogonal linear polarizations. The intensities just add, so there's no gradient in the total intensity, but the relative phase of the waves undulates in the transverse plane, so we have helicity fringes, and this will, I promised, will accelerate your opposite molecules in opposite directions. So finally, I'll very quickly outline three applications for this, three devices. So device number one is what we call a chiral Stern-Gerlach deflector. The idea here is to work in the Newtonian regime and employ a single helicity fringe, pass your molecules through. If the molecules are left-handed, they'll be deflected to the left. If they're right-handed, they'll be deflected to the right. So with the possibility of optically separating enantiomers. Putting numbers to that, it seems the deflections will be small, but certainly measurable. But in order to get into this regime, the flux of molecules through the device is likely to be so small, this is not going to be used on a large scale to separate enantiomers, which is, as David said. So that takes me to device 2 now. The idea is to work in the much more sensitive de Broglie regime, and we're more interested in measuring the properties of chiral molecules. It's metrology. So you pass your matter waves now through a collection of helicity fringes. They diffract, and the diffraction pattern is the same for left and right-handed molecules. So it doesn't distinguish between left and right, but it does tell you that there is a distinction in the sense that a similar achiral molecule will exhibit no diffraction. It doesn't see the helicity fringes. And these diffraction patterns are very sensitive to the chiral geometry of the molecule. So hexahelicine is shaped like a little spring. If I imagine reducing the pitch, so flattening the molecule, the diffraction pattern changes. So if I half the pitch, that's a change in molecular dimensions of the order of an angstrom, the diffraction pattern changes its form completely. The 0th order, which was at 25%, has now vanished, and the first orders, which were absent, are now up at 25%. It's a very clear change. And of course, if I flatten the molecule entirely, it's no longer chiral, so I get no diffraction. So finally, device number 3 is a combination of device number 1 and device number 2. We add a shadow mask to obscure certain parts of the helicity fringes. It's like a blaze grating now. And that's enough to give you a discrimination, like we had for device number 1, and sensitivity, like we had for device number 2. So it's a marriage of both, the best of both worlds. So my final slide now. We're interested in molecules, of course, which are very small objects. But I should say that the next speaker, Etienne, has performed experiments with larger objects that have demonstrated the use of chiral light to manipulate the center of mass motion of chiral objects. So this is a real thing that can really be done. And what was it you said? We have to climb and you have to dig. That's it in terms of scale. So thank you very much.
Is there a quick question? Please.
Where did you submit the stegosaurus paper?
So it's currently with Journal of Vertebrate Paleontology.
That's awesome.
Thank you.
That's, gosh, that wasn't quite the official we had expected. Is there another quick one? If not, okay. So thank you, Rob. Let's move on.
Does not work. Okay, anyway, I will do this by hand. Okay, so good morning everyone. So the connection with 2 previous talks is actually quite straightforward. The introduction has been made. So being aware about this session organization, I deliberately skipped a few slides on chirality introduction. This has been done by both previous speakers. Here I will jump directly to experiments Two previous talks were setting up a framework to deal with chirality in terms of light matter interaction towards optomechanical effects, for example, with sorting applications, chiral resolution with light, but from a theoretical point of view, with a focus on molecular scale, so let's say nanometer scale. Here, as has been shown in the last previous slide, it's fine for this. I will jump to micrometer scale, and this work actually corresponds to the PhD study that has been done by Georgi Tkachenko, now at St. Andrews with Kishan Dolakia as postdoc. So let me start with a quick introduction with what has been done so far from an experimental point of view, but not with light. First, recent studies with the idea is to induce discriminatory forces on chiral objects at microscale using external fields, actually helical fields. The first example here is in a microfluidic channel with appropriate patterning to create an helical flow, let's say of water, in which is injected some particles which are chiral. And those particles, the left-handed and the right-handed microparticle, will be separated in space after a few after a given distance. The same year, 2 years ago, under this time rotating magnetic field, so it's a static, quasi-static magnetic field under rotation, and the idea was to rotate magnetized helicoids. The head of the helicoids were magnetized. It's magnetic material, glued, if you wish, with an helicoidal shape tail. This way, applying a external magnetic field, you have a propeller effect and chiral separation between left-handed and right-handed species, as shown here in the experimental pictures. Then, more recently, actually very recently, rotating electric field can induce actually a separation in space using this time molecular scale elements. Using a molecular dipole moment, so it's permanent dipole on molecular scale, and here you can see the enantiomeric excess, which means the way you enrich a given chiral form with a huge separation time, which scales with tens of hours. So the context of this work is to go actually to work with light and to get rid of this need of propeller motion. Actually, because all these three experiments were dealing with the appropriate use of coupling the mechanical degrees of freedom, linear and rotational, so which means mechanical chirality, if you wish. So the idea is to use the rotating part of light, so in this presentation, the helicity of light, without propeller effect, to address chirality, but without the help of a chiral shape, really dealing with the chirality of the molecular entity. For this, we will have to deal with something which is typically spherical, for example, no helical shape. This way you get rid of, I would say, macroscopic propeller effect. And the idea is to use a chiral scatterer and to illuminate it by chiral light. And if you have an helicity-dependent scattering, you may expect helicity-dependent optical force exerted on this chiral scatterer. So to do this, so we have to choose experimentally towards an experiment. We need to choose a chiral material. We choose liquid crystals, which is shown here in a non-chiral mesophase, nematic phase, in which if you add some chiral dopant, chiral molecular, you get an helical supramolecular ordering. In that case, you can have a strong light matter interaction that depends on the helicity. Helicity being left or right, propagation can be allowed or forbidden into the system if you propagate along the helical axis of the system, of the material. And the experimental manifestation of this strong helicity-dependent effect is shown here. This is natural light transmission spectrum. When you propagate along this helical axis, as you can see, there is a band gap where half light has been reflected, as shown in this picture here. So the idea is to embed such helix, supramolecular helices in a sphere, and this will be our particle. So it will be inhomogeneous chiral object. So to do this, we take a glass of water, a nematic drop, a little bit of chiral dopant, you shake it really by hand, mechanical steering, and you get an emulsion of droplets. And if you look closely to those droplets, they are nicely self-arranged because of the liquid crystal self-organization properties in this way. This is just artistic representation of a droplet. And here you can see here, this line corresponds to the helical axis. You have a radial distribution, if you wish, edge-like distribution of the helical axis of the liquid crystal molecules inside a microscopic droplet. And the idea is to use this droplet to get the experimental observation of discriminatory chiral forces. The idea is the following. We have millimeter scale beam waist Gaussian beam, circularly polarized, left or right, impinging on a small, I would say, 10 micrometer diameter particle, and you expect a force which depends on helicity. And these discriminatory forces can be, I would say, quantified introducing this C parameter, which is the chiral force contrast. Let's call it like this, which means that how much the induced velocity by this force, how much is different depending on the helicity, which can be, let's say, Bragg reflection, or anti-Bragg, which means the opposite helicity. If it's 0, it means non-chiral discrimination. If it's 1, it's full discrimination. So one beam experiment here, we measure in practice the two velocities, V anti-Bragg and V Bragg, and we report the ratio. The ratio is non-zero, which means you have a discrimination. The discrimination factor is typically alpha. And this is the summary statistics over a huge set of droplets. So this ratio is well defined and well understood from analytical description that I won't present here. If you want a full control and to get towards a full discrimination for this optical force and to get close to 1, the idea is to cancel this residual, I would say, a standard scattering event here, adding a second beam with the appropriate helicity. In that case, when you tune only the helicity of one of the two beams, you get a full control over the velocity that you induced. And in that case, you can start from 0 here, if you have the perfect balance, and then increasing power, switching the helicity and increasing power. You can really have a full control, whatever the radius, this is independent of the radius, a full power control, which is well understood. The solid line being the theoretical adjustment without fitting parameters, actually. The idea then is to use this towards a few kinds of applications. The first of them is sorting, not sorting moleculars. This is, let's say, kind of gray. Sorting those particles. You got a set of left-handed and right-handed ones. Could we apply these discriminatory optical forces to get optomechanical chiral resolution? And the picture is shown here. We have to use this two-beam setup. So we have two beams, same power, and importantly, the chirality of the two beams are fixed. They are not changing. And then you play bowling. You take a one droplet and you launch it in between those two beams. And you have a look, what is going on. If it's glass beads, let's say, non-chiral, then it is expected that when the bead enters in the interaction area, it will see the same kind of field, same kind of interaction. So it will be pushed the same way by scattering force. So it will go straight forward. In contrast, if it's left-handed, it will experience a more important scattering from the left than from the right. And then you have a deviation that is associated with the chirality of the particle. If you reverse the chirality of the particle, you have a reverse motion. And I insist, the field is fixed. So there is no change. It's passive sorting system. So we realized the experiment that has been just depicted just before. For left-handed particle, you just launch it in a channel, in a capillary. And let's have a look what is happening. I need to click. I'm not lucky. So the particle trajectory is going like this. Hopefully I will be lucky with this one. No. No. So it will be the same. And for non-chiral particle, it goes straight forward. So I'm not lucky because I missed my video, but I got the summary. And the summary gives you snapshots of what is happening in these 3 videos. So here you have a capture, so it's just superposition of images. And you can see that when you enter in the interaction region, the camera grasps the residual scattering. And then you can see you have deflection. The deflection depends on the chirality of the system, non-chiral particles being shown here. So you have a fully passive optomechanical chiral resolver. fewish. And now we are moving towards chiral sorting in microfluidic system, microfluidic chamber. Because actually those particles which are micron scale suits well for being embedded in a micro channels, which are typically few tenths of size here, this transverse size. And the idea is to get some flow like this, and with these two beams configuration, you have an efficient 100% passive sorter at microscale with high throughput. So this experiment is presently running in the lab. So soon I should be able to show you some results. But this is the principle. And why we were going there? The idea is then to go towards molecular scale sorting. So to go nanometer, of course, this scattering force, this was part of one of the discussion, the one question which was asked by Wolfgang, this annoyed by Brownian motion at molecular scale. Our idea here is that imagine those large chiral particles, imagine them as trucks, chiral trucks. And the idea is to load the trucks in a selective manner with nanoparticles, with nano entities. Be they chiral or not, actually we don't mind. Here, let's say triangle and spheres. If you have, like, let's say, selective binding between these blue and pink trucks, since the trucks can be efficiently sorted with 100% probability, then you just need to release what you have bind, and then you have a full sorting at the nanoscale. So it's indirect nanoscale sorting in that case. So this is one of the options we would like to explore. The second kind of application started with fundamental, I would say, proposal. The proposal is summarized here. So in the previous talk, we had a few words on, of course, Pasteur and the introduction and this picking up by hand, so with mechanical tweezers, macroscopic tweezers, to sort tartaric acids crystals, right-handed or left-handed. So he had first to recognize them, so first step, and then to make an action and to select them, to pick them by hand. The proposal is to replace this recognition step plus this action by a man by using a tweezing with chiral optical tweezers. So the idea is you have a tank with left-handed and right-handed particles. You can close your eyes, you have your tweezers, and the tweezer is, let's say, right-handed, my right hand, and this is light. I go into the tank, and by 100% chance, I will pick the right-handed one, because I will be trapping, I will trap selectively the right-handed particle. If I change the tweezer, so I change the helicity of the light field, so now I got a new trap, I do the same, I will, in that case, pick up with 100% efficiency the left-handed particle. So the idea is to realize this with light from these chiral discriminatory optical forces. So to realize a demonstration of it, we used two counter-propagating beams to realize a 3D, I would say the simplest way to get 3D optical trapping with big particles, large particles. Because remember, we are dealing with particles typically 10 micrometer diameter. So the two counter-propagating beam interaction, which is well known since the early 70s, suits very well for that. So you get selective trapping, and we can describe the force in 3D, and we can even, this I will convince you that we can validate experimentally that we get actually a 3D selective trapping. Here, this is the case of a Gaussian beam with a given combination of optical and material chirality. If we launch a droplet, this is the trapping point. We launch a droplet here on the right side. This is the force field. It will be just going to the trapping point. We record experimentally the velocity from which we can deduce the force, the longitudinal component of the force. We do the same launching the particle from the left side, and then we can reconstruct the full longitudinal force component. So data, statistics of experiments with model. The same for the transverse case. In that case, you drag by hand the particle displacing simply the tank, the sample, over the trapping area. And then, looking at the deviation from the dragging velocity, you record this, from which you deduce the radial contribution. And you can reconstruct, doing some statistics over tens of events, you can reconstruct such a shape. So if I summarize, I got this. In the longitudinal direction, I got negative slopes, which is well known to be signature of stability. And in a transverse coordinate, I got such also negative slope. So this is invariant per rotation around the z-axis, which is here, which means I got a 3D trap. And this works also for vortex beams. So this leads me to it's 5, so it's perfect, as here, 5. So discriminatory optical torques. So these are very fresh results, so they are not yet published, so, but still I would like to share first results we get there. So it's extension of these discriminatory optical forces to torques. Because why not restrict on forces when we are speaking with optomechanics with chiral particles? Uniform forces is a displacement, but distribution of forces is a torque by definition. So quite naturally, we want to address this question. Could we define a chiral torque contrast that we would define this way, that the difference between the light-induced spinning velocity under whatever light field, and looking at the difference of the magnitude divided by the sum of this magnitude of rotationally induced effect. If it is 0, as the usual case, let's take the standard birefringent particle that has been discussed in the previous sessions in several talks. So if you send left-handed, let's say you will have left-handed spinning motion. If you have right-handed, you will have right-handed spinning motion. The magnitude will be the same. The particle is birefringent, is non-chiral, no expectation to break this degeneracy between left and right-handed magnitude for the light-induced rotation. We would like to have such a situation. A discriminatory torque means, let's say in the perfect case, C equal 1 means that for a given helicity, the system is not responding, and for the other helicity, the opposite helicity, the system is spinning at a given finite rotation rate. To do this, we will use again this cholesteric liquid crystal chiral system, remembering the following, we sketch here, reflection from a standard mirror. It's well known that if you have a circularly polarized light carrying plus or minus h bar per photon, it will be reflected with the same amount of angular momentum with respect to a defined axis in the lab. However, if you use chiral Bragg mirror, in that case, as we showed in the first slides, light can be forbidden, propagation forbidden, or allowed. In that case, in one case, you have absolutely no momentum deposition. In this case, you have 2 h bar per photon deposition at reflection. So when you use droplets, it will be in homogeneous situation, quite more complicated, but we have the ingredients. So experiment is the following. The idea is to have a droplet which is free to rotate this time at a fixed location. We don't want to look at translational motion. So the idea was to use a vortex upright like this, and to have the droplet like a kind of funnel of light. The droplet is coming, and if the waist is small enough with respect to the size of the droplet, the object will be trapped by the vortex beam. And then we just have to follow the rotational motion. So it is, camera is from top. As you can see, you have an image. But if you look at this image, which is looks ugly, but still it contains the information. This homogeneous pattern is, I would say, rotating. You have here the few snapshots, and if you do correlation, autocorrelation of this image with time, you will have such a trace, time trace, from which you can derive the Power spectrum, and some frequency is emerging. And from this, you can assess that for one helicity you have rotation, and with the other you don't have. So I will stop here. This is a summary of what I've presented. Summary is that the first point is optomechanical forces, from which we derive two kinds of applications, sorting and trapping, which are selectively dependent on the chirality, and a new, I would say, opening a new door with a rotational spirit. Thank you for your attention.
When you make your droplets, do the pneumatic molecules kind of spontaneously become chiral and either rotate?
How it goes? What is the question exactly? I don't
I
catch.
was wondering how it is that droplets become chiral when you make them.
The point is that when you mix a nematic, you can see it as rods, let's say, to make it simple. A collection of rods, which are, so the nematic liquid crystal mesophases. You have a set of molecules, anisotropic molecules, at the scale of the molecular. And then every molecule is parallel to the other one. So this is what is happening locally. If I add some chiral dopant, so another molecule, let's say my end is here, these objects, the rods, need to adapt with my end. So if you reach there is some molecular chiral interaction that makes, I would say, from one molecule to another to have a slight twist in terms of the average local orientation. And this leads at the microscopic scale to a supramolecular ordering. So this is self-organization. The experimentalist has not to arrange this helix at the macro scale. It is self-done by the material system. So this is properties of this long interaction range of the liquid crystals. So we just benefit from it.
I have a question about this chiral torque. And last year we calculated torque on a chiral dipole particle, and in generic optical field it's proportional to the Poynting vector. So if you put a chiral dipole particle in optical field with some Poynting vector, opposite chiralities will rotate, will spin in the opposite directions. Is this somehow related to?
I would say no. Because here we don't need this. What you are talking about is with an interaction with a dipole,
yes,
with an entity. Here it's the interaction with a macroscopic assembly of chiral dipole, if you wish, of those molecules,
yes,
plus some surrounding. So it's mesoscopic at the mesoscopic scale here. In that case, it's a little bit different.
So I'm interested in the optical torque. The rotation seems incredibly slow because it's minutes. I noticed. How can you be sure it's not just Brownian diffusion or an asymmetry in the intensity profile that's causing that?
Simply by switching the. If you change the chirality of the droplet, for example, you will have the opposite rotation with the appropriate spin. So actually, you can make every test because you have every test. You have two parameters. You have the chirality of light and chirality of matter. You have 4 combinations. And those 4 combinations have one results. If you can check these 2x2 matrix expectations results, you're done. So we are sure it is not. And if you use just a glass bead, it stays. And importantly, this minute rotation speed actually comes from the very decision to use a vortex levitator. Because vortex levitator means there is no intensity on axis. And the main part of the helicity-dependent light scattering comes from the on-axis, I would say, part of the micro-object. So actually, because of this Laguerre-Gaussian profile, the interaction part is quite small. And so the minute rotation speed comes from that.
Splendid. So let's thank Etienne again. And our final speaker.
Right in. Cuprous oxide happens to be a long-standing material of great interest because of the excitons. The work I'll report was done with a former student of mine, Nguyen Kohang, and also with 2 people not mentioned here, John Lee and Professor Tu of our department. So jumping right into it, the talk is going to quickly pose the issue of measuring, well, this is a theoretical talk, so predicting measurement of the exciton spectra.
Sorry, I think this must be the power supply.
Oh, okay, so I am.
With any luck.
Go back in, there we are. Measuring the excitons, and I guess I better get out of the way. Measuring the excitons in this material, and then using the ability to impart angular momentum to create what I call change from a dark exciton, forbidden, to a observable exciton. So here, zooming right down to the microscopics, and here in this slide, we're sketching the resonance or absorption regime of this material, cuprous oxide. By the way, it's been worked on for at least 80 years, and the puzzle of what is still to be learned, I'll come to in 1 second. Now, you'll notice the black dot is where an electron is. That's the conduction band. The highest or upper valence band is the white dot. The symbols, gamma 6 plus, gamma 7 plus, are group theory jargon giving us the classification of these states, which contain not only the information about angular momentum, but also how the crystal field of this crystal, which is cubic, changes the designation or labeling of the states. You'll notice particularly both of the states, the 6, if I can get it there, 6 and the 7 are plus, meaning positive parity. You'll also notice the existence on the right of a sequence of discrete levels standing for the hydrogen-like sequence of exciton levels, which by agreement occur in, they're not agreement, but actually under, measured up to a point, it occur within the gap. And in particular, the excitation that we're interested in here is the 1s, that's like hydrogen labeling. 1s yellow refers to the pair of levels involved in making this exciton, and you might, for some of you, find it easier to think positronium, but this is a bound state electron and hole in the material, and the para refers to the spin configuration. But what is most of importance for us is that both valence and conduction, I seem not to have stepped on this. Now, what did I do? Sorry? No.
Skip too many slides.
I saw back up. There we go.
Coming back.
There we go. What is important is that the parity sign plus is the same for the two entities that make up this exciton. Now, because of the parity being the same of electron and hole, the resultant quasi-particle has, as described here, positive parity. As you see on the bottom here, same parity for the two states involved in this entity. A little detail is shown here for group theory aficionados as to how we reached that conclusion. Now, because of the excitation having positive parity, you see on the lower right part of the slide, you have actually a description of the wave function of this state, and it is designated para-exciton. Now, coming to, so there it is, the gamma 2 positive labeling. Now, the significant issue, which has actually been touched on by both previous speakers, particularly first speaker of the session, is that there are selection rules connected to the existence of expansion of the radiation operator and the radiation matter coupling operator. And make a long story short, the para-exciton, the 1s yellow para-exciton, is strongly dipole forbidden. It is not quadrupole or electric quadrupole or magnetic dipole allowed, so it has never been observed in a direct optical one-photon transition. We know of its existence because it participates in indirect transitions assisted by other quasiparticles in this cuprous oxide material. So I now come to, again, I seem to be too far ahead of the game. Yes, but I want another. I don't understand why I'm not showing the tracing of. Next one? Nope.
He's in the wrong buttons.
See, it's not moving from here, and it should be showing.
Should we come out of the show and see if it's where the rest of the paper, where the rest of them are?
Oh, the problem. Okay, well, let me just say, I'm going to give a quick verbal statement of what we should be seeing on the slides. Having posed the problem that the direct transition of one photon creating this state, 1s yellow para-exciton, the next step, how can we use the complex light, in particular Laguerre-Gaussian light, to solve this issue? And what I hope will come up in the next slides within the time allotted before everybody runs out to lunch. There we are. Okay. So this summarizes what I said and gives one more bit of detail which I like to point to, namely the expression of this yellow exciton wave function. Here's the spaceport, which you see is of 6th degree in the Cartesian coordinates and actually corresponds to orbital momentum L equals 6. And here is the spin port right tacked on there. Now, this entity, which is the wave function of that dark exciton, has gamma 2 plus symmetry. That's a representation of the cubic, full cubic group, well known to those, as the saying goes, who know a bit of group theory, and is the reason for this highly forbidden, down here you see this, highly forbidden dipole and quadrupole transition. So we come to now the use of the Laguerre-Gaussian beam, and in this work what we did was actually following what Professor Andrews said in the first talk. We introduced into the Hamiltonian of the radiation and exciton, we introduced an interaction term using minimal coupling, the vector potential for the Laguerre-Gaussian beam taken in this form. It is, as expected, a little bit complicated, but not so bad, including angular momentum and the radial dependence of the Laguerre polynomial type. And so we then set up the interaction term. Again, please note A dot P, P dot A term, and some detail follow on this slide, following which I have a slide showing the, first of all, the interaction, and then breaking the total matrix element into components of these operators. following which we have the new selection rule that careful study of the matrix element gives us. Namely, turns out there are two channels allowing the matrix element to be different from 0. One, an L equals 5, another, an L equals 6 channel. Both of those apparently are operative. So this is the state of our present calculation. I had hoped at this point to be able to report on the relative intensities or line widths of absorption, one photon absorption through either of these two channels, but we did not complete the numerical work, and so I would ask anybody interested to please stay tuned, and if you are a cuprous oxide aficionado or an exciton aficionado, then hopefully we'll have some quantitative results fairly soon. The work is in progress. So the bottom line is that using Laguerre-Gaussian light, we can, in this model, impart the needed angular momentum to cause, the theory predicts, to cause one photon absorption, changing a dark exciton to a loud, bright exciton. How bright, I'm afraid I can't tell. I apologize that the calculation is not completed. The work is in progress. And I thank everybody for your attention, and hopefully I've stayed within time so that everybody can enjoy your lunch. Again, thank you.
Since there are really not much cleaner crystals, I think, available than cuprous oxide, and there have been so many studies on the photoluminescence from this exciton line, don't you think that possibly the fact that nobody has observed it is a proof that overlapping momentum does not participate in quadrupolar transitions, actually?
Well, on the contrary. The cuprous oxide, as I say, goes back, studies of it 80 years at least. Within the last 3 months, 2 papers came out of the Dortmund group. Professor Dietmar Fröhlich, who is an expert in this field, and again, to tickle interest in this subject, the first of these 2 papers, published late last year in Nature, shows that a Rydberg exciton, meaning a state of the electron and hole with n, principal quantum number, up to 25, n up to 25 has been observed, and of course n equals 1 is absent. Beautiful experiment, recent. I urge people interested, take a look. The second paper discusses the achievement of high states of angular momentum in the yellow series. So these angular momenta states going beyond the usual SP, etc., going up to states H with up to n equals principal quantum number 7 have also been observed. Why? Well, amazingly enough, Fröhlich and his collaborators point out very explicitly they used a particular dirty crystal from a mine in Africa. Everybody in the world, including theorists like myself, think that the most beautiful crystals have been made artificially by vapor deposition or by some other tricks, but these colleagues have used this, it's all in the literature or a preprint. If you look up Dietmar Fröhlich?
Yeah, I know that work, of course.
You know this recent work? Okay, so the answer is high angular momentum, not, in fact, including L equals 4 has been observed. What we still need to know to really do the physics of this is the line shape. I mean, who cares? You might ask, who cares? You know indirectly that this 1s yellow para-exciton is there from experiments that were done, in fact, at City College by a colleague not living now, Herman Cummins, and we need to know more detail of the line shape and temperature dependence, et cetera, of this line, and that's why I think that encouraging this kind of measurement to make the dark light would be most useful. And thank you for your question.
So, no more quick questions. So before we thank all our speakers, let me remind you about the photograph and then lunch. And let's, as I say, thank all of our speakers for a really splendid session.
You just said nobody did with the gases.
That's